Hello and welcome. In this video, I'll be working through the first part out of 2 for the Unit 7 test review. So my hope for this video is to help at least give you an idea of how to begin or start each question, and just provide a couple of different ways maybe to approach or think about how to go through and do each of these. So the first part primarily just covers the first 3 sections. So that involves the sum and difference formulas, the double angle, the half angle, as well as being able to simplify using trig identities or even prove trig identities. So that's essentially everything that this review will have practice for, so hopefully this is helpful. So let's go ahead and start with the first group of 4 here, which all just want us to simplify. So remember, with simplifying, we're just trying to make something turn into a little bit cleaner or more efficient looking version. So oftentimes it will turn into just a single term. Sometimes it might still be a couple of terms, but again, ultimately our approach is to basically try and make things look better. So how we approach them is we just start looking for things specifically from our identity sheet that we could maybe replace. So with this first example, as we can see here, hopefully, that the 1 plus tangent squared of theta does resemble one of the Pythagorean identities. That specific one right here will actually get to be replaced with secant squared of theta. So I'm going to go ahead and just approach it that way, and then everything else I'm just going to keep the same. From here, I hope we could recognize that secant is a version of cosine. I just have to do its reciprocal, so I could flip it, keep the power, so it's basically utilizing a reciprocal identity here. And now I think we would hopefully see that cosine squared of theta divided by cosine squared of theta will cancel each other down, and in fact this one just simplifies down to a simple 1. So again, not the only approach for this one, but I think that's probably the most efficient way of doing it. A second way of doing it would maybe be going after the parentheses and distributing the cosine squared through. I would probably then want to replace the tangent squared with a sine squared over cosine squared, so I could maybe even do that first and then distribute the cosine through, which then we would see the cosine squareds would cancel out. And then more than likely I'd end up with a different Pythagorean identity that I would substitute into the problem, and more than likely just turn into 1. I believe if we did it that way, it would turn into cosine squared plus sine squared, which I think we would maybe recognize as that has a value of 1, and we'd still arrive at the same location. So this one, again, 2 different main approaches that I can think of off the top of my head that both would turn into a value of 1 in the end. For number 2 here, this one being a fraction to start, I feel like we should probably just try and simplify as much division as we can. Since there aren't any addition or subtraction signs, I know I should be able to just do top to bottom canceling as easy as possible. So for this one, I would go ahead and say the 30 and the 6, let's just divide those down, see what they turn into. So 30 divided by 6 is a 5. And then from there, let's just see one thing at a time. Let's start with maybe the signs. So I've got sine cubed on top. I have divided by sine on the bottom, so that's going to leave me a positive sine squared of x in the numerator. And if we go ahead and look at what else is left, it looks like I've got a couple of cosines. Those ones should be able to reduce as well. And if I go ahead and reduce those, I end up getting a cosine that would stay on the bottom, so I know I have over a cosine of x. So my first instinct here is to maybe try and find a way to get that cosine to the top. I could rewrite it as a secant, but that doesn't really seem like it's cleaning things up, and that would keep a power of 2. So what I'm actually going to do is utilize one of those signs and put it over the cosine that's on the bottom. Since that actually does have an identity, that should be able to turn into tangent, and then leave the other sign off to the side. So again, just kind of splitting up that power of 2, and at this point the sine of x over cosine of x I could replace with tangent of x, and then times the sine of x. I feel like that right there is probably the best version that we got, or at least it would be the version I would think makes the most sense for this as far as the simplifying step. But technically we could go ahead and maybe go with the other version, which would have been, maybe I can call it just 5 times sine squared of x times secant of x if I were to just move the cosine that was on the bottom up to the top. That also seems to be about the same in appearance. The only thing that kind of stands out as using tangent. Notice I didn't have a power of 2, whereas using the secant, I did keep a power of 2, so I still think this top version seems a little bit nicer than the second version there, but when it comes down to it, ultimately I would likely accept both of those results because I can't really go any further without making things worse with either of those two. So that would be one of two possible solutions that I would accept for that one. Moving on now to number 3. Number 3 here, I think we would likely all see pretty quick that we have a bunch of even numbers that it looks like I can probably factor out. The fact that I see powers also is something that's kind of lending me towards I probably will want to factor. So I'm going to go ahead and just factor, looks like in the top I can factor a 4 out, and that would leave me a sine squared of x plus 2 sine of x plus 1. And at this point I would go ahead and say on the bottom, let's factor the 2 out, and that would leave me a sine of x plus 1. So it appears that the 4 and the 2 that I have on the front, I should be able to reduce to a 2 and a 1. Now I also recognize, like when I factored the 4 out of the top, that looks like it created a quadratic, so I should likely be able to factor that. The 2 that I've got out front is just going to stay out front. But I'm hoping that when I factor this on the top, that it will maybe match one of the factors that's on the bottom, or the only factor that technically is left on the bottom. So here it would just be what multiplies to 1 that adds to 2. Well, that should be just a pair of 1s, so this should factor into a sine of x plus 1 times another sine of x plus 1. Again, that gets me the 1 at the end, but it also would give me a middle term of sine of x plus sine of x for a total of 2 sine of x. And I do, in fact, get this sine squared in front if I did the sine of x times the sine of x by FOIL. So here, notice now whatever was on the bottom actually cancels with one of those factors on top, so it appears to me that the simplified version would just be 2 times the sine of x plus 1. Because I can't really replace anything there. I could make it a 1 over a cosecant, but to me that seems like it would make it worse. Or the other option would be actually distribute the 2 back through and get rid of the parentheses. So again, I could say it's, as it currently looks, the 2 parentheses sine of x plus 1, or I could make it 2 sine of x plus 2. Both of those, again, would be acceptable responses for this one, but kind of the key for, I guess, the start of simplifying this one was just find a way to factor and reduce as needed. In this case, it was kind of nice that the factors actually reduced pretty quick and turned into what we ended up having. As for number 4, first thing that kind of stands out to me are the negative signs on the inside of each of these functions. So I'm going to go ahead and just deal with those to start. The only functions that would be able to kind of eliminate those negatives would be the even functions, which are cosine and its reciprocal secant. So since both of these are odd functions, I know that the negatives actually would just be able to move out front, just utilizing that odd property that each of these functions happens to have. And at that point, now those two negatives are out in the open. They can interact with each other. A negative divided by a negative would actually just turn into a positive, so I can just say this is the same as a cotangent of theta over a cosecant of theta. So I've at least dealt with part of the ugliness. At this point, what I feel like I should probably do is just maybe start moving things around. I'm not a big fan of this being a fraction, and with cosecant in the denominator, that's not too tough to make it turn into something that's not a fraction, which would just be move it into the numerator and it turns into its reciprocal, which happens to be sine of theta. So it's slowly starting to make a little bit more sense, but I still don't really have the ability to interact with these two, or at least have any way of combining them. So now my next instinct is to maybe try and replace the cotangent with what it's equivalent to, but kind of thinking about I want it to be able to interact with this sine. So what's kind of nice about the cotangent is I could turn it into a cosine of theta over sine. So even though we did just get rid of a fraction, and now I'm bringing a fraction back in, the whole reason why I'm actually doing that is with the intent of hopefully something will get to maybe cancel, whereas before when I had the fraction I didn't really have the ability to cancel, hence why I tried to get rid of it. So here now notice I've got sine of theta on top and on bottom, so that technically has left the most simplified version of this, which is just a cosine of theta, and so that would be my final result. So again, is that the only way through these problems, at least as far as the simplify is concerned? No, there are multiple routes through it. It's just this is what my first instinct is, so hopefully just at least seeing one way to go through it is at least helpful when it comes to thinking through like what approach maybe should I try when it comes to maybe doing these on my own. All right, the next group of questions now will want us to specifically prove identity. So a little bit more direction on these. Remember, our approach for these is basically pick a side and just try and manipulate it as much as I can until it turns into what's on the other side. So for number 5 here, just first glance, I feel like the left side seems like a better starting point than the right side. But again, when all else fails, just pick a side and try some things out, and just keep in mind where you're trying to go towards. So again, if I'm going to start with the left side, I have tangents to begin, but it looks like I need to turn into sine of 2 theta. And if I think ahead, sine of 2 theta would be like a 2 sine of theta cosine of theta. So if I can make sines and cosines start happening on the left side, that should get me going in a direction that makes sense for the right side. Now, other things that I kind of noticed right at the beginning is I do have a power of 2, which makes me think a Pythagorean identity is maybe something I would want to try and use. In fact, that actually is a decent start to this one in my opinion, so I'm going to go ahead and just go after trying to make the 2 terms on the bottom turn into 1 term, and that 1 term would happen to be secant squared of theta. So again, 1 plus tangent squared of theta is the same as secant squared of theta, so I've just replaced that with its value. From here, I'm going to go ahead and deal with the secant that's in the denominator and move it to the numerator and turn it into a cosine squared. And the reason I'm able to do that is because cosine is the reciprocal of secant. So if secant's on the bottom and I want to move it to the top, it just will need to turn into its reciprocal, which happens to be, as I just said, the cosine of theta. I just keep the power of 2 when it comes down to it. So now I'm going to go ahead, since I've kind of created the cosine, now I'm going to try and replace the tangent in terms of sines and cosines as well. So if I replace the tangent of theta with what it's equivalent to in terms of sines and cosines, it would be sine of theta over cosine of theta. And that's still multiplying with cosine squared of theta that we've gotten from replacing the secant squared in this step before. I think at this point we can see that we have a cosine in the denominator that will cancel at least one of the cosines in the numerator. So that now off to the side here will turn into 2 sine of theta, still on top, but then times the 1 cosine of theta that's left. And wouldn't you know it, that actually is the same as the double angle for a sine of 2 theta, which is exactly where we were trying to head. So at that point, we've been able to show that the left side was able to turn into the right side, so we've proven that this identity does in fact hold true. Now with number 6 here, kind of seems like the same general thing. I'm going to start with the left side, hope that I can turn it into the right side with relative ease. I'm going to go ahead and find a way to maybe think of how I could maybe deal with that fraction first. So similar to the last example, I see that power of 2 and I immediately think maybe I can use a Pythagorean identity. Cosine squared, if you recall, is the same as a 1 minus sine squared. And I feel like there's probably going to be some way if I have a 1 minus sine squared in the numerator that it might be able to cancel somehow, some way with the 1 plus a sine of x that's on the bottom. So that's actually going to be how I get the ball rolling with this, is just replace the the cosine squared of x with 1 minus sine squared of x, and then just keep it over that 1 plus sine of x that I have on the bottom. Now what's a little bit different than maybe some of the examples we've done, I don't know if we've maybe seen this, we've usually gone the other direction, but what I can do, since the top is a difference of 2 squares, I can actually factor that conjugate, or factor that into a conjugate pair. So the 1 plus sine of x again will stay on the bottom. But if I wanted to multiply to get this 1 minus sine squared, remember when I have a difference of 2 squares like that, I end up getting a conjugate pair as the product or the factored version of that specific thing. So 1 plus sine of x and 1 minus sine of x should give me the same as 1 minus sine squared of x, because again the middle terms would cancel out And why that's actually helpful is if we notice what now is on top and bottom, I technically have a grouping of 1 plus sine of x on top and on bottom, so they can reduce each other down. What gets a little bit tricky, and this is where I think most mistakes will happen, is I need to make sure that this minus sign that's in front of this will distribute through. So for the time being, it might seem a little bit silly to leave the parentheses. I'm just going to go ahead and do that and just add one extra step here that reminds me, hey, I do need to actually distribute that minus through. And at that point, I think we would see 1 take away 1 would in fact zero out. And that now just leaves me sine of x, which is exactly, again, what I was trying to make happen, as we can see right here. Now on to number 7. So number 7 wants us to, once again, prove the identity. So I feel like the left side getting turned into the right side, or trying to match the left side with the right side, is the smarter approach. So kind of the same as the last two, just start with the left, make it turn into the right. Reason being is there's more stuff happening on the left, so I hope that seems reasonable. I'm going to go ahead and kind of go after the let's make everything sines and cosines approach. So replace the cotangent and tangent with their equivalent statements. So sine of theta, parenthesis, and then cotangent's the same as cosine over sine. Tangent, on the other hand, is sine over cosine. And at this point, just distribute through and eliminate the parentheses. So if I distribute the sine of theta through the two terms, the first one, the two sines are going to cancel, and it just leaves me cosine of theta. The second one, though, I end up getting a sine times a sine in the numerator, so that actually will be a sine squared of theta that then stays over a cosine of theta. So now I've got something that's a fraction added with something that's not a fraction, so my next instinct is let's get a common denominator. Since the cosine is technically over a 1, I'm going to go ahead and just say, you know what, if I multiplied by cosine of theta on top and bottom, that will technically get me the common denominator, so I can now make this all one single fraction over cosine of theta. What I would now have, though, as far as the two terms, cosine times cosine would give me cosine squared of theta, added with the sine squared of theta that was already over, or already in the numerator of the second fraction. And I think at this point we might recognize that these sine squared and cosine squared, if I add them together on top, will turn into a 1. That's one of the Pythagorean identities. So I get 1 over cosine of theta, which happens to equal a secant of theta, which, just like before, is exactly what we wanted to turn into. So that concludes this specific proof. And now moving on to the last proof that we got, number 8. This one, again, probably going to deal with the left side, but this one is almost more of a 50-50. Both the left side and the right side kind of seem like they're equally difficult, at least as far as the starting point. So I think I'll show this one just by choosing the left side, but there is a way to do it if I chose the right side that probably is about equal in level of difficulty. But anyway, I'm going to go ahead and just go with my first instinct, start with the left side, see if I can turn it into the right side. First thing I notice is this left side doesn't have sines and cosines where the right side does. So my initial thought is let's go ahead and get some sines and cosines involved. And that actually was kind of convenient because once I did those two substitutions, notice we already have a common denominator. So I'm going to go ahead and just combine them and make it a single fraction, so it's starting to resemble what the other side is. It just seems like it's flipped and has the wrong operation. So some options that we could do from here is now just thinking ahead. I know that that has been able to turn into this. Let's maybe just force some action. I need to get a 1 plus cosine of x on the bottom, so let's just maybe force that to happen. And as long as I do it on top and bottom, or multiply top and bottom by the 1 plus cosine of x, that's the same as multiplying by 1, I now can just see maybe what the results would turn into. So on top, a 1 minus cosine of x times a 1 plus a cosine of x is a conjugate pair, so that should just square both terms and keep subtraction in between. So that would turn into 1 minus cosine squared of x. On the bottom, since I don't really want to change the 1 plus cosine of x, that's kind of what I was trying to go towards anyway, I'll just call that sine of x times the 1 plus cosine of x, or in other words, I'll just keep it in that factored form for the time being. in hopes that maybe something on top will cancel this sine of x that I have on the bottom that's a little bit extra. And I think we maybe at this point have seen this 1 minus cosine squared of x enough times that we've now maybe recognized the Pythagorean identity is something I probably want to use. Again, powers of 2 usually are a good indicator of a Pythagorean identity is going to be used next, or somehow, some way get involved at least. And here, if I replace the 1 minus cosine squared of x with the sine squared of x, notice I now have a sign that's on top that can cancel with the sign that's on the bottom. And that now leaves me a single sine of x on top over the 1 plus cosine of x that I wanted to have only on the bottom. And so that now has shown that it came around full circle and turned into the right side. So that, again, closes up the proofs for the identities as far as the approach. Just to reiterate and give you an idea of how to start, it's just pick a side and start trying to replace maybe just one thing at a time. Sometimes, like this example, I replaced both parts on the left side, and it kind of opened up an avenue. So again, just think through, like, if I do this, what is that going to look like? Do I maybe want to do a second thing at the same time because it's helpful? And ultimately, it just kind of comes down to the more you practice it, the easier it is to think through what those options are and hopefully choose, I guess, the correct substitution to try. But when in doubt, at least start trying something. Pick a side, go until you get stuck. Don't erase it. If you still don't know what to do next, maybe start trying it with the other side and see if you can maybe work with it for a little while. And if you get stuck there, hopefully where you got stuck in both cases happen to match. And you can kind of just work your way backwards through whatever that process is, depending on which side you wanted to have your final answer deal with. But again, try and make sure that you're only starting and utilizing one side and turning it into the other side. Do everything in your power to try not doing it with manipulating both sides, even though maybe the answer key from the textbook did do that. I'm wanting you to do more of a, let's just only choose one side and turn it into the other. Just be forewarned, I guess, when it comes to how that's going to be graded when it comes to taking the test. Now moving on to the second standard that this test will have. Again, everything that was just covered, all of the simplifies and proves, those were all just our first standard for that test. The second here is now going to be more of all of the formula-driven things, so like the sum and difference, as you can see here, or a double angle or half angle. So this may involve some references to unit circle, or it may involve just drawing some triangles, kind of depending on how the problem's being presented. So the first couple here, as you can see, are going to just want us to use sum and difference formulas, so having those at least easy to identify somewhere close by on your reference page, just so you know exactly what you need, should likely get you set up for success. Now the first thing we want to do is try and figure out how could I make whatever angle they have provided for me that they want me to find the value of. How do they break that down using either a sum or a difference? So 75 degrees, my first instinct is to just do 45 degrees plus 30 degrees. But again, that's not the only option. We technically have a lot of different ways that we could create 75 degrees. I just think if I can stick with angles in the first quadrant, that's probably going to be easier for me. Now if I go ahead and follow the formula, I've kind of at this point identified that all of the A's in the formula are going to be 45 degrees and all of the B's in the formula are going to be 30 degrees. Now I just follow what the formula says. So the first one would be, let's do cosine of the A, so 45 degrees. Multiply that with cosine of the B, so 30 degrees. And then I subtract sine of each angle. So sine of 45 degrees times, and then sine of 30 degrees. At this point, it would just be replace each of these with their ratio from the unit circle. So if I go ahead and do that, cosine of 45 degrees is going to give me square root of 2 over 2. Cosine of 30 degrees is going to give me square root of 3 over 2. Then I subtract sine of 45 degrees is also a rad 2 over 2. And then sine of 30 degrees is actually a 1/2. What's nice about these is they already have a common denominator of 2 times 2, so I'll just combine it, make it a single fraction over a 4. And it looks like I've got square root of 2 times square root of 3 to make a square root of 6 from the first fraction, and a square root of 2 times a 1 from the second one, which is a square root of 2, and subtraction stayed in between. So for this one, square root of 6 minus a square root of 2 all over 4 would be my final answer for what the cosine of 75 degrees would be. Number 10 here now is going to be pretty much the same approach. I still want to use a sum or difference formula, but key difference here is instead of degrees, now I have radians. So to start, I might recommend just trying to figure out how could I make this 17 pi twelfths by just thinking of it as a pair of fractions that have a pi on top and 12 on the bottom that add up to create that 17. So first numbers I kind of think of off the top of my head are a 2 and a 15. But technically I guess a 9 and an 8 would work, but I'm choosing numbers intentionally that would reduce with the 12s on the bottom, so hopefully when I do the reducing, which I'm going to do now, 2 over 12 would reduce to a pi over 6. Notice that turned into an angle that we recognize hopefully from the unit circle, and then 5 and 12 share a 3, so I can divide each by 3 and get a 5 pi over 4, which also happens to be an angle from the unit circle. So at this point, I have the ability to rewrite this as sine of pi sixths plus 5 pi fourths, since that I just showed was the same as 17 pi twelfths. But now I actually can think of it as two angles being added together, and I've got my A and B now identified, so I can just follow the formula. Now again, that isn't the only pair of angles that would work. It just happens to be the first pair of angles that I came up with. If I chose the 9 and the 8, 9 twelfths would reduce down to what, 3 pi fourths, and then the 8 would have turned into what, 2 pi thirds. So I could technically use those two angles for my A's and B's in the formula as well. But let's go ahead and continue on with this. Let's just follow the sine sum formula. So it wants me to do sine of the first angle, so sine of pi 6, multiply it with the cosine of the second angle, so 5 pi fourths. Then add that with, this time I'll do sine of the other angle, so the second angle is 5 pi fourths, and multiply that result by cosine of the first angle, pi 6. So the second term, really the key is as long as I either switch the angles or I switch the order of sine and cosine, it should work out. So maybe on your formula sheet it might have cosine first and then sine second. It doesn't really matter because it's a product. As long as I have the two things, it should still work itself out. So now it's just to a point where I replace with their values from unit circle. So sine of pi 6 happens to be a 1/2. Cosine of 5 pi fourths, that happens to go into the, what is that actually, third quadrant. So that's going to be negative rad 2 over 2. Added with sine of 5 pi fourths, also negative rad 2 over 2. Multiplied with cosine of pi 6, which is a rad 3 over 2. So if I now simplify, well, just like before, they have the common denominator of 4, so I can just put it over a 4. 1 times negative rad 2 gets me a negative square root of 2. Added with a negative rad 2 times a rad 3, that's just going to give me another negative, this time rad 6. So final answer for this one would be negative rad 2 minus rad 6 all over 4. Or I could technically rearrange that, make negative rad 6 go first, then minus rad 2 on top. Or I could even factor a negative out if I wanted to. So there's a couple of different ways to write our final answer, but as long as it would be equivalent to what I currently have there on the screen, it would be a-okay. Moving on to now number 11. This one wants us to still do a difference formula specifically. This one wants me to just figure out what cosine of u minus v is, but it's not giving me really any angles to break down. This is just giving me a couple of ratios. So first instinct for me is let's go ahead and just draw a couple of triangles for each of those ratios. And I'll just call one of them the u angle, the other one the v angle. So it does say specifically that both of these are between pi and 3 pi halves, so that would be quadrant 3, or the bottom left side of the unit circle. And so that means I know that my horizontal and my verticals both are going to have negative signs. Remember, the diagonal or the hypotenuse of each of these is always going to be a positive value. So from the first ratio, it says cosine of u is negative 4/5. I know that the horizontal or the adjacent side must be negative 4. Hypotenuse is 5, and that's a 3/4/5, so I know that I get a 3 on the other side. But again, it's in the third quadrant, so it's got to be below the x-axis. On my vertical edge here, I'm going to go ahead and make that a little bit more obvious, is a negative 3. Second one, cosine of v gives me negative 2/5. So once again, my adjacent would be the -2, the hypotenuse would be 5. This time it's not as nice of a 3, 4, 5 triangle. I actually have to do Pythagorean theorem, so I'd square both those numbers and subtract. So 5 squared 25, -2 squared is 4, 25 take away 4 is 21, so this would be the negative square root of 21, once again because it's in the third quadrant. I know the vertical edge must also be negative. Now for the cosine of u minus v, if I just write out what that formula is just using those letters, it would be cosine of u, cosine of v, minus, actually no, not minus, but plus sine of u, sine of v. I just now need to figure out what each of those ratios are and replace them with their values. So cosine of u, if I look at what we got, would be -4/5. It actually was one of the ones provided for me. Then I go to the next one, cosine of v would be the other thing they provided for me, so -2/5. Added with sine of u, that's something I needed to find from the triangle, so that would be -3/5. And sine of v, similarly, I need to find from the triangles, would be the -rad21/5. So this looks like we've got a common denominator of 5 times 5, so 25. And if I simplify, I've got -4 times -2 would give me +8. And then I've got two negatives here, so that'll also be a plus, and this time 3 times square root of 21 I can't really do much with, so I'll just call that 3 square root 21. So final answer for this one, if I just go ahead and put it over here so it's a little bit more separated, 8 plus 3 square root 21 all over the 25 that we just found. On now to number 12. This one kind of similar to the other one. We can approach it actually a couple of different ways. This one says to do secant of pi halves take away theta. If we recall though, this actually is one of those identities that's a cofunction identity. Secant actually would turn into its cofunction, which is cosecant. So cosecant of theta is technically what this problem wants. So the fast way through this problem is now go, well, if I know that sine of theta is equivalent to this -3/4, and I need to know cosecant of theta, it should hopefully be as simple as all I had to do is flip that ratio since they're reciprocals, so -4/3. Let's say maybe that connection didn't work out though. What I could have also done is just drawn our triangle here to represent at least my theta angle. I know my opposite side must be -3. My hypotenuse must be 4, and it does say quadrant 3, so I know my horizontal leg would also be negative. And so square both of those, I get what? 16 take away 9, because I would need to subtract. 16 take away 9 would give me 7, so square root of 7. But quadrant 3 means it would be negative. But notice that side, actually for what it was asking me about, I wouldn't necessarily need to know. I just needed to know what the cosecant would be, which we're actually just using the two numbers they provided already. So again, maybe I would need to have the triangle, but this specific example didn't have to know. Again, that's where kind of thinking about how can I connect this. Had this been something or a different approach, let's maybe we didn't recognize the cofunction, we could have utilized, we could have switched that, I guess, into 1 over cosine of pi halves minus theta, and then use the cosine difference formula, and then flip that result, and we eventually would have got to -4/3. That would have been a significantly longer route through the problem, still would have got there. So again, always look to see is there maybe a quick and efficient way that I can replace or answer this question without having to take a super long route through, utilizing maybe an identity I didn't have to actually use. So again, moral of the story there is if you see something that you recognize on the formula sheet, might be beneficial to try and use it right off the bat. This one though happens to kind of match two different things. I have a difference inside, but I also have the cofunction. So again, that one can be a little bit tricky, especially if the identity was presented in degree format, not radian format. If it said 90 degrees instead of pi halves, maybe recognizing that that is a cofunction would have been a little tougher to see. But again, as you have more experience, you can kind of see or at least think through our options. This one had two different options. I would say the second option, this one here, I would say is gonna take a little bit longer, still would work, but definitely was way faster when I just called that the cosecant or utilized that cofunction identity. Now for 13, it looks like we need to this time do one of the double angle formulas. So for that one, if we think ahead of what we got, that one actually has three different options. With this one having only given me cosine, I could technically go straight to just utilizing the 2 cosine squared of theta minus 1 version of that and just plug in the value that they gave me. So in this case, -5/13. Square that result, take away 1. So if I go ahead and square each of those, it's going to turn into a 25 and a 169. So I'll probably need a common denominator of 169, so I'll go ahead and get 1 rewritten using that. And if I double that, I get 50 over 169, take away 169 over 169. And that should give me a negative 119 169ths. Different approach we could have done, since there are 2 other versions, is we could have technically taken the given info, so again back to the cosine here, went ahead and drawn a triangle to represent that angle or to be able to utilize that ratio. I know that my adjacent would be the -5, my hypotenuse would be the 13, and then if I go through and do Pythagorean theorem, I would find that the last side of that is 12. It is a quadrant 2 angle, so that would be a positive vertical side, so positive 12. And then I could have utilized maybe the cosine squared of theta minus sine squared of theta, and then approached it a similar way from there. So if I just substitute in its place, it would be the cosine -5/13 being squared, then take away the sine, which is 12/13 being squared, and I'd end up with 25 minus 144 over 169, which gives me, if I were to combine it just in a different way, a negative 119 over 169. So again, 2 different solutions or 2 different ways to do it. We technically have a third that we could use, which uses the 1 minus 2 sine squared of theta. So it really just kind of comes down to just pick one and go. I initially saw that since I had cosine, I could just go straight to using the one that had only cosine and not have to worry about drawing a triangle, but notice there was still an alternate way of doing it. So hopefully one of the 2 that I've shown here actually makes sense. As for the last one on this review, number 14 wants us to do a half-angle identity specifically. This is one that even if we tried doing a sum or difference formula, the 8s that are in the denominator would basically be impossible to have both reduced down to angles from the unit circles. So I'm kind of forced to use the half-angle formula. So I need to figure out what is 5 pi 8ths half of. Well, 5 pi 8ths would be half of 5 pi 4ths. So I really could rewrite this as it's like cosine of 5 pi 4ths all over a 2. As far as location is concerned, 5 pi 8ths is a little bit more than 4 pi 8ths, which is like pi halves. So this is actually a quadrant 2 angle. And if we look at our formula for the half angles, there's a plus or minus symbol that goes in front. So even though I'm going to reduce it down, the plus or minus, because of the second quadrant, is going to tell me that I want to keep the minus. I don't want the plus. So in fact, I'm going to go ahead and just get rid of that really quick and just know that it's going to keep a negative in front. Now as far as what goes in the numerator, cosine uses the 1 plus cosine of the angle that is being cut in half. So in this case, that would be the 5 pi 4ths, and then it's all over 2. So now it would be just replace the cosine of 5 pi 4ths with its value. So in this case, 5 pi 4ths is a third quadrant angle that happens to be in the middle, so that must be a negative. And then the middle ratios are always rad 2 over 2's. And so now I've created the fraction inside of a fraction situation that's popped up a few times in homeworks. So distribute through a 2 to get rid of the 2 that's here on the bottom. And that gives me now a negative square root of 2 minus a rad 2 if I go ahead and deal with the plus and negative in the numerator. And then 2 times 2 on the bottom would give me 4. And now just apply the radical from the big portion of this to both the top and the bottom. And the top will just stay that. The bottom, on the other hand, square root of 4 would actually turn into a nice 2. So my final answer for this one would be the negative square root of 2 minus rad 2 in the numerator all over the regular 2 on the bottom. So hopefully this video has been helpful and giving you at least some plan of attack for each of the problems that will be on the first part of this test. If there are questions or you need extra examples, just come find me and we can try and figure them out or work through some others. But yeah, anyway, I appreciate you taking the time watching this. If you have, we'll catch you next time.